All right, welcome back to part 2 of electric potential difference. In this video, we're going to be looking at electric potential in circuits and electric potential difference, and looking at an analogy that's going to help us understand this concept a little bit better. So in the last video, we looked at electric potential, which we understood as the amount of electric potential energy at a certain location. It was only dependent on location. It did not depend on charge. It was the amount of electric potential energy per charge at a certain location. So now when we are looking at a circuit, and specifically we're going to start looking at a battery powered circuit. They're the easiest to draw, easiest to understand. So a battery powered circuit will have locations of high potential and locations of low potential. And so if we see here on the diagram here, this diagram over here, we can see labeled on this battery, a nice big chunky 12-volt battery, there is a location of high potential and a location of low potential. The high potential being at the positive end, the positive terminal. This is where we have the most energy. Right? The most energy here is at the positive terminal, the positive end of the battery. Another way to say that, it has the most voltage or the most joules per coulomb. Right, at this location, there's the most joules for every coulomb of charge. And then the location that has the lowest potential is at the negative terminal. This is where we have the least energy. Or we would say it's the least amount of joules per coulomb of charge. And to move a positive charge, we're going to be talking about the movement of positive charges, which is the flow of positive charges in a circuit. This is something called conventional current. We'll talk more about that in a future section, but we're going to be talking about positive charges flowing. So the movement of a positive charge through the cells, through a battery, from the negative terminal to the positive terminal, to get that there, it's going to require some work. If you remember back to, I'm not sure when you learned this, but this idea that positive or like charges repel, opposite charges attract. The positive terminal, where the positive charges are flowing to, if there's positive charges there, it's going to be repelling any other positive charges that are coming its way. And so it takes some work to actually push those positive charges together in that direction. And so if we're doing work on these positive charges, we're going to be increasing their potential energy. And so every coulomb of charge has a certain amount of potential energy increased. That means it's there, the positive terminal, there's going to be some voltage, some amount of joules per coulomb at that location. And so to talk about electric potential difference, well, a difference is simply a comparison between one location and another. The difference, it's a subtraction type of idea between one location and another. So to move a charge from location D in this circuit here to location A, work will have to be done by some external force. And what's the source of that external force? Well, that's what the battery is actually doing. The chemicals in the battery, there's some chemical process that is doing work on these charges to quote unquote lift, to move these positive charges from location D to location A within the battery, right? This is the direction that these positive charges are flowing. So work is being done to move those charges there. And so the work done on the charges changes its potential to a higher value, and the amount of work done is equal to the change in the potential difference, right? So the change in the potential difference, how much potential it has at location D compared to how much potential it has at location A. Remember, delta means change in, it's final minus initial. Final location is location A, the positive terminal. Initial location is location D, the negative terminal. So the difference in those is equal to the work done to move these charges from negative to positive, or we'd say it's the change in the electric potential energy per charge. Notice this equation looks almost identical to the equation that we had in the last video, where it was voltage is equal to electric potential energy per charge. But now we're saying that there's going to be some change. We're not always going to go from 0 to some number, 0 to 5 volts. We might go from 5 volts to 10 volts, but there's going to be a change in potential, an electric potential difference. Okay, so this is what we call voltage. When we're talking about electric potential difference, this we call voltage. And so to reiterate this idea, 1 volt is the equivalent to 1 joule per coulomb of charge. Now, what's the whole purpose of this? Well, the whole purpose of this battery doing work on these charges to lift them, quote unquote, up to this positive terminal is just like gravitational potential energy. We can lift some mass up to some height, and then we can release it, and that gravitational potential energy that is gained by us lifting it can be converted into kinetic energy, for instance. When we lift a charge to the positive terminal of a battery, then we can let the charge flow, fall through the wires to the low potential terminal, and in doing so, it will flow here on our diagram, flow through the circuit, through some circuit elements such as a light bulb in this example, and use its potential energy to power those circuit elements, right? Run the light bulb, run your stove so you can cook your food, play your music, power your computer, whatever it is. That electric potential energy will flow through the wires, flow through the circuit until it's used up that energy. And then it will have to, those charges will have to go through the battery again to get charged back up, to get the energy back up so they can flow through the circuit again. A nice analogy for this, if you want to think about it, is like a water park or some water slides. And thinking about the water that is going to flow through a water slide. And so we think about the charges that are flowing through a circuit as the water that's flowing through a water slide. The water, to go down the water slide, has to get up to the top of the water slide, right? So there has to be some sort of water pump. That's our battery, right? The battery is lifting the charges, our water pump is lifting the water. And the circuit elements, the different things that the charges are flowing through to power, our light bulbs, our stove, whatever things that we're running, those are like the water slides. The whole point of pumping the water up to the top is so that they can go down the water slides. All right, here's going to be my crude little picture. Here's our water pump. Right, here's our pump. And here it's going to be pumping some water from, here's the pool of water down here at the bottom. You're going to crash down in. And it's going to take the water from this pool. It's going to pump it up to the top. And we're going to have, here is our water slide that goes down into this pool at the bottom. Perfect. I'm such an artist. Thank you. Right? And so here's our pump. It's going to pump the water up, give the water gravitational potential energy so that the water can then flow down. And then once it's at the bottom, it's out of gravitational potential energy and it needs to get pumped back up to the top for it to go through again. Right? Our pump is our battery, the water is our charges, and the water slide is our circuit elements. The loss of electric potential while passing through a circuit element, we often refer to this as a voltage drop, right? A loss of energy for every coulomb of charge, a drop in energy, which if we think about that in terms of a water park analogy, that makes a lot of sense. A voltage drop, an energy drop, it's a physical drop in a water park. It's not a physical drop. Your circuit doesn't literally have to be constructed vertically for the voltage to go down, but it will lose energy as it goes through some circuit element. We call that a voltage drop. And by the time that a charge has returned to the negative terminal, it started at the positive terminal of the battery, it made its way through the entire circuit. By the time it's returned to the negative terminal, it is at 0 volts. It has lost all its energy, and it's ready to be re-energized, pumped back up to the high voltage positive terminal, and go through that whole circuit again, right? So if a particle might have 10 joules of energy, by the time it's done going through the circuit, getting to the bottom, the negative terminal of the battery, it has no more energy. It's used it all up. And that's conservation of energy. That's something called Kirchhoff's voltage law. If you want to look that up, Kirchhoff, try and figure out how you spell that. It starts with a K, but that's the idea. It's conservation of energy. All the energy given to a particle will be used by the time it's done going through that circuit. Okay, that's it for this video. Next video, we're going to just look through a couple examples of electric potential difference and charge and potential energy, and then looking at something called electric potential diagrams. See you soon.